As you know, they're not going to miss anything. Hi, you guys, if you watch this. So, make this move. We already went through this first part. On Friday, we had talked about, delta, the change in the concentration over the change in time is rate. And you're going to subtract the final minus initial concentration, final minus initial time, and you get a rate, and everything's fine. And that was cool, right? No problems there. And notice that when we were talking about a reactant, it is by custom that the rates have to be positive. So when we're talking about a reactant, we're going to put a negative sign in front of that just so that, well, obviously the amount of a reactant is going to go down during a reaction. It's going to turn into products. You don't have to do that with a product because it's going to increase. So it's going to be positive anyway. This was a crazy slide. I made all better. Yeah, it's okay. Instantaneous rate is slope of tangents. You guys in calculus right now, I was talking to Jordan, and if you want to seem like a genius, I don't know if you actually seem like a genius, but just for fun, like you were having to like look at something, and like she asked if that stopped or whatever, what was going on right there, and the line that's tangent to that point has slope of 0. So at that point, you have an instantaneous velocity of nothing. So you should tell her that because that was a question. You can't argue that. I think it's totally right. Me and my non-calculus, right. Anyway, tangent line, instantaneous velocity. If you look at the slope of this, these little curves here, you can tell that NO and NO2 have the same coefficient. Oxygen is going about half as much, and hey, that works out, right? So it tells you about the amount that's getting produced. We did this example, did a little math with that for the rate. Looks crazy, not really that bad. So here's where we are today. So this is completely separate from Friday. Okay, this is a whole other way of doing stuff. We're not doing delta stuff. We're not making slope lines. This is not the same. Okay, when I looked at this stuff this summer, all these things I got in my head and had this big fat happy family party, and I failed to make them discrete pieces of information, separate pieces of information. So the rate, when I'm looking at this rate law is just saying a way of writing out the what's happening in the reaction in a formula basically. So the rate is equal to K. K is different for every reaction. You're not going to find K on your formula sheet. Every reaction has a different K value, and it's going to change depending on the temperature, because faster reactions are going to happen when you heat it up. It's going to go slower when you cool it down. So this is only at one particular temperature is this K going to be true. And so notice my first reactant is raised to a power. If it's a 0 order for the reactant A, then that's a 0, or it could be a 1 or 2. There are half-order reactions. You can have 0.5, 1.5. We're not going to have to do any of those. You can also have stuff above 2. We don't have to do those. So fine, whatever. But for our instances and for our what we're needing to do, we're looking at 0 order, first order, and second order. We don't need to do any half orders. You're fine about that. Don't freak out about that. That's not a thing for us. Anyway, so the order in terms of A is in, and then in terms of B is in. Notice in this rate law, I'm only dealing with reactants. So on your quiz you just took, right? That question I won't talk about it because I haven't taken it yet. But that should have been pretty simple because what were you only have one reactant, so that was the only possible rate law. Okay. So reaction orders. They cannot, I cannot stress this enough, and I know the notes that I gave you stressed it, and I'm going to say it again. You cannot tell the reaction order from the balanced equation. Okay? If it has a coefficient of 1, that does not mean that it is first order. If it has a 2 in front of it, that does not mean second order. You cannot tell this from the balanced equation. You cannot tell the reaction rate from the balanced equation. I know that I showed you some lines. We said that oxygen was about half as steep as nitrogen dioxide or whatever. Well, that's cute, but like at some point, I had to know the rate of something to compare. Like, and I can't get that from the actual written balanced equation. Can't get that. Purple stuff's clear again. It's almost all clear again. Ooh, magic. Anyway, so can be 0 for second order. So in our instances, 0, 1, and 2. Other things are possible, not important for the AP exam for us. This is going back to what I made you guys do on Friday. Okay, I made you spend all that time looking at exponents, not for fun, but because it was going to be important for today. This K value right here, like I said, it could be anything. But I think that if you don't know what it is and you're just trying to look at something, it's helpful to just think about it as like 1, right? So if the rate is equal to K, and let's just make the constant 1 for this reaction, it's 1 times a to the 0 power. Well, anything to the 0 power is what? 1. So the rate is going to be equal to K. Okay? Now, if K was 17 million and A was 11 billion raised to the 0 power, this whole thing right here wouldn't matter. K would just be equal to the rate. Doesn't matter. So when you have a reactant and we find that it's a 0 order, what its concentration is has no bearing on the actual rate. So the rate will be equal to K, and that's just because this guy right here is always going to equal 1. Doesn't matter what number's in there. Anything to the 0 power is 1. Okay? So rate is just going to be equal to K. If I double the concentration of reactant A, it doesn't matter. It's still going to be 1. So rate is going to be equal to K. You good there? Okay. Notice that if I'm looking at a graph here, a plot of concentration versus time will produce a straight line for 0 order reactions because the rate isn't going to change when the concentration changes. So, not a straight line. This whole straight line thing with concentration and then natural log concentration and then 1 over the... I got that. Don't worry about that yet. This is hitting on that a little bit, but we're going to look at those graphs a little bit more tomorrow. Make that real easy for you. But basically, here's concentration, here's time. It's just going to go down at a steady rate. Okay? Nice straight line. First order reactions. Now, anything to the first power is itself. 2 to the first power is 2. 10 to the first power is 10. Okay? So, if I'm looking at rate equals K times A to the first power, what I'm going to get is just rate is equal to K times whatever that concentration is. If I double this concentration, I'm going to double the rate. Let me make that. Let's give these some numbers. Can we leave K 1? I like 1. 1's a good number. If my concentration is 2, then my rate is going to be 2. I'm going to go back to green. Yay. That's a different color green. Number. Sorry. If my concentration, there's my 1 power. If my concentration's double, then my rate's going to be 4. There's my rate again. You want me to make it green? Sorry. My K value is not changing. Is that the same color green? Sorry, Todd. You don't know what I'm talking about. I'm so bad for you. If I double my concentration again and go to 8, then my rate's going to be 8. So this is just going to go up for whatever factor that goes up. If I double the concentration, I'm going to double the rate. If I triple the concentration, I'm going to triple the rate. Both sides of this they're getting multiplied by the same number. Multiplied by 2, by 4, by 8, whatever. They're going up at the same factor. You okay there? All right. And then we only have 1 kind left, so that's not too bad. Second order, when I double the concentration, I'm going to quadruple the rate. If I triple the concentration, I would, whatever times 9 would be the rate. So, do y'all have a question? I heard things. No. So doubling the concentration of that species quadruples the rate. So notice that my power on my concentration here is a 2. And so let's get some numbers again. Let's go back to 1. So 1, 1, 1. Those are my K's. I'm just setting them up, right? And I'm going to make it equal to my rate. And now I'm just going to put in some concentrations here. Let's just start. I guess we can do 1, right? And then this one we'll do 2. And we'll do 3. So 1 squared is 1 times 1 is 1. So my rate would be 1. Well, 2 squared is 4 times 1 is 4. So notice I doubled my concentration, but right here this went up by a factor of 4. Okay, 3 squared is 9 times 1 is 9. So I tripled my concentration, but this went up by a power of 9. If I quadruple my concentration, this is going to go up by a power or a factor of 16. So basically, the rate goes up by whatever that factor that you increased the concentration of, it goes up by that square. So when I double something, that goes up by 2 squared. When I triple it, it goes up by 3 squared. When I quadrupled it, it went up by 4 squared, which is 16. 5 would be 25. We're not really going to see numbers that big. But that's all there is to those. That's pretty straightforward. You're getting kind of bored. That's good. That means you already get it. Now you're not going to be bored very much longer. That's it. That's it. I did get a couple questions about. Did I go backwards? Oh, I totally did go backwards. There. So the overall order. Let's give these some numbers. You know, if I find that reactant A is 0 order and this is, you know, 2nd order, then the overall order of the reaction would be 2. Okay? So if I found that this was 1st order and this was 2nd order, the overall reaction order would be 3. Are you guys okay? You're making sounds. Did you miss something on the quiz and now you're sad?
No, I thought I missed.
You didn't? So if I got this to be 0 and this was 1, the overall reaction would be 1. You just add them. Okay? This is about to be really important when we look at units. I got like 3 emails about units over the weekend, so ta-da. Don't forget that these brackets are molarity. And, you know, if this was by power of 1 and this was, you know, 2nd order there, then I have 3 capital M's working over here when I'm looking at my units. You see it? They're getting multiplied together. That's about to be really important. So far, are you okay with what happens with one reactant with the other and as far as the rate goes? 0, 1, 2. Okay. So here's where some of you guys were getting to be a little bit confused. I want to just, these charts with all the letters, this is very intimidating, okay? So I want you to do me a favor. I'm just going to clear the screen, and I'm just going to, let's give you a couple things to look at. And I just want you to work with your group. These are just concentrations. Just, you know, off to the side. I want you to work with your group and just tell me what the units on this stuff would be. Just real quick. Shouldn't take you more than 30 seconds. These are molarities. These are getting multiplied together. No, I want you to tell me the units. So would it be a capital M, perhaps M squared, perhaps M cubed? Yes, it's molarity.
I think the first one would be yeah.
That's what I was just thinking.
Third one?
I was just thinking about that when you multiply something.
Yeah. Yeah. Yep. When you multiply stuff, you add exponents. Yay. Or you just add them up. I mean, you're adding. This is it. Yes.
Are you asking for like units for the concentration?
Yeah.
Or for the rate?
So the rate always has the same. Rate always has the same. Thing. So no, I'm asking for this stuff on the board. I'm laying a little path here, and I'm gonna make it go down with me in a minute. All right, so I was just looking at a release exam, and it was like, what is the units on this? Blah blah blah. And so they really like to ask what the units are for each order of reaction, and then you can either like memorize it. Not that you're not gonna have a lot of other things to memorize for the AP exam. You can figure it out the way I'm about to tell you, or you can sit there and work the problem out. So I'm gonna go with this. So anyway, like I said, I'm not done trying to show you stuff. I'm just laying that groundwork for you. So Jordan, what's the units on this gonna be when I multiply it?
I said it in squared.
Yeah, because this is just gonna be something molar times something molar. That was foot times foot. You'd be like foot squared. That was 0 problems, right? For whatever reason, we get into chemistry, get different letters, and your brain doesn't work so well. Jacob, what's the units on the second one? Yay! Piece of cake, right? And if I just had one bracket with nothing, of course it would just be an M, right? So Amelia, what's that third one? Yay! Are y'all cool with this?
Yeah.
Okay. Now, not done yet, but just if these are my reactants, and then these are their orders, this would be first order, first order. It's gonna give me M squared. Now this is not the overall answer, like I'm not done yet, okay? This would be second order as well. Second order. This would be third order, okay? I got 3 capital M's, yeah? So that's part of it. Now, if I'm looking at reaction rate, don't even look at the board. If I'm looking at a reaction, we did this on Friday. When we take something and we're measuring a reaction, we're going to have molarities over seconds or what? It could be minutes. But it's basically, the general one is just how much concentration per unit of time. Molarity per second, or moles per, no, molarity. Concentration, that's where concentration per second. Like a rate for a reaction has to be concentration per second. It has to be. Now, is my rate for this reaction, is it just those 2 things multiplied together? What am I missing? I'm missing that K thing. That K thing is multiplied by these guys, and then that gives me the rate. And that rate has to be concentration divided by seconds. Okay? So let's look at that. You know what? Let's not even look at it yet. Stuff like this, people can't handle it. So there's K. If I want to get out, if this is what I'm trying to get out, if that's what I'm trying to get out, what does this K unit even need to be? Think about it. Talk to you people. Talk to you people. Figure me out some stuff. And here, let me give you this one.
It needs to be orders, polarity, orders.
And
it'd be, I think it'd be
Oh, you got you.
You have to write the units with the negative exponent?
It would be weird not to. And they're not going to write it like this. They're going to use the negative exponents. I don't like it either.
I know what it means, but
I don't like it either.
I don't
That's
like
how they
looking at
do.
it that
They save
way.
paper. I don't either. I don't like it, but that's how they're going to do it.
can I like write it like that
On your answer, if you're doing free response, sure. But know that when they showing you, they're not going to do that.
It's like I know what it means. I
Like to cancel stuff. Absolutely, absolutely.
Because that's what I was doing in my head was canceling. So
Yeah, exactly.
I can't do that.
Have y'all kind of got stuff to cancel for you? Yeah? Okay. Whee! Bennett, you're up. So tell me what K is going to have to be in order to get an M and an S out of this. M over S. Sure. And if we break this up, gosh, I feel like I'm in college again doing student teaching for math. I remember those days. It was fun. Because this means, right, that's what that means. So, and I'm left with M over S. So, for second order reactions, the unit on K is equal to M -1, S -1. That is that. If you don't like those negative exponents, then too bad, because that's what they're using. Okay? I'm sorry. That means it's on the bottom of the fraction. Yes. You can totally write it like that, but they're never going.
That's how advanced is all I feel like that.
Yeah. Like on a free response, you do whatever you want. But, I mean, as long as it's equivalent. But they're not going to do that. So second order, and look right here. I'll tell you the little, I made it like a little thing up, but I'll get to that. So this one's going to be the same, right? For third order, Clint, what you got?
Like, you're talking about
To make it cancel to be meters over molarity per second.
2 M's left on the bottom, so it's like M squared on the bottom
Sure.
times second.
Yeah, sure. And so this is the unit for my K. And then I get out of that this, which is what I need for a rate. Concentration over a unit of time. So for second order, for third order, I have M -2, and then I got S -1. And that just means, hey, I got an M and a 2 and an S on the bottom. Okay? Now for first order, do you want me to do this one? Can I do this one? Sure. Right? Does that cancel? Oh, no. Just kidding. I know the answer. I knew the answer already, so I was like, yay! Okay. So anyway, now I'm left with, this is what I was trying to go for. And that's what I want, right? So it's just S -1. That's it. Okay? Now here's how to do this. You ready? Here's like the trick. You ready for the trick? Okay. The trick is, let me start with third order. You with me? For third order, the molarity is 1 less than the order. Inverse, second inverse. Second order, molarity is 1 less than the order, and it's inverse, right? So that's going to make it a negative. Second to the negative. Again, 1 less than the order. Well, 1 less than 1 is 0. Okay, so that makes that go away. Right? Anything to the 0 power goes away. So first order, m to the 0, so it's not even there. And then second's inverse. So they all got a second to the -1. And then that m, this has 1 less than the order. So I got a chart. If you didn't get that, like I got a chart, okay? But that chart doesn't mean anything if you can't look at it. So this is what I just did with you. For first order, it's 1 less, and then seconds. Second order, 1 less, and then seconds. And then third order, 1 less, and then seconds. For a 0 order, that is where K is equal to the rate. And you know what rate has to be. Has to be molarity per seconds. This is molarity per seconds. We didn't even have to do nothing to that. That's just what a rate is. It's concentration per time. How do you feel? You good? I'm just gonna give you like a minute to just not think for a second. Just take a little break. Take a little break, get another cookie, do whatever you want to do. Look at the purple stuff. It went away again. All right, so Yeah, this would be the place where you need to go get that quiz. Hello. Alright, so like I said, this is a little bit easier to start with than the one in the PowerPoint, so I'm going to start here. This is like my favorite kind of problem, and I don't know why, but I really like it. There's a really long, drawn-out mathematical way to do this, but it's also equally legitimate to do it by inspection, which means by looking at it. And if you write the right sentence, you'll get the points, and it's fine. And the right sentence sounds like, when the concentration of A doubles, the rate also doubles, so the order in respect to A is 1. When the concentration of A doubles, the rate quadruples, so the order in respect to A is 2. Like, you can say it like that, or you can do the rate laws for both of the experiments that you did. So these are like trials. Trial 1, whatever. Trial 2, and then trial 3. And so, you know, what chemists can do is they can run an experiment a couple, 3, 4, 7 times, and then they'll compare that initial rate as they mess around with the concentration of the different reactants. And you're actually going to do this in lab on Wednesday, which is pretty cool, I think. So, what you have to do when you're doing these is you have to find from one trial, like this one trial, to the next trial, only one concentration changes. So A stays the same, so cool, and then B changes. So trial 1 to trial 2 is very handy for looking at upon inspection for the order of B. So if I look here, then I can see that the concentration of B doubled. And these are always going to have like crazy, stupid exponents. Like, throw those out in your mind. Okay? Look at the powers of them. Okay, this is 8. Notice that this is 1 more and that's 1 more. So I'm looking at 8 and 16 and 32. So 8 and 16 and 32. And the way I can tell it's 8 and not 80, again, look at this is smaller than these. So this is a power of 10. Like, there's my decimal. The decimal is 1 smaller. So there's that. All right, anyway, so this doubles in respect to B, and then the initial rate doubles. So in my rate law for this, what number do I need to put in my exponent?
1.
Yeah, because this doubles, they do the same thing. That's a rate order, just 1. Okay. Now I got to figure out A. So if I'm looking from trial 1 to trial 3, I see that A doubled, B stayed the same. So 8 to 32 is actually quadrupling. So when A doubles and the rate quadruples, then I have raised that factor by power of 2. So what do I have to raise A by? Yeah. So what is the overall order of this reaction? Yay. What would be, without looking at anything, what would be, now this ain't the whole thing, I got a K here, right? And then I got a rate. What you guys were getting confused on when you were emailing me about these crazy, you know, you were like, well, I don't understand why the unit isn't just concentration per time. We're not talking, this is always concentration in the amount of time. Well, what the crazy units go with is K. So I got 3 M's hanging out. This is going to be an M over an S. Okay? So what's that unit of that M got to be? So I got M, then I got -2, right? Or is it go here?
On the other
I think because I wrote it so close to itself, I was like, what am I doing? Sorry. I just scrunched it up. So M and then -2. That, yeah. It just looked weird. I was like, this is the wrong answer. And then an S, they all have S and -1, and because that's on the bottom. How do we feel? Sorry. Yes.
One thing that confused me, I understand looking for the first part, but
Yeah.
then looking for concentration A, like going from trial 1 and 3.
So you just ignore that second one.
Because you know how like for trial A, 2 and 3 it doubles. And then for, I don't know, just
Do you know that you don't even, when you're looking from 1 to 3, you just ignore this middle one? That doesn't even exist when you're looking from 1 to 3.
How'd you know to look from 1 to 3?
Okay, so I figured, were you cool when we did B? Alright, so I gotta look and I'm like, well, I have to find one where B doesn't change. You have to find one where this one doesn't change, and this one does.
Okay.
So, and then you see what happens, this double, and so. How does that make you feel? On the multiple choice, on the like the real exam stuff that I've looked at, the numbers are very easy to look at, and that's about right. The numbers, what I'm about to show you, a little bit more complicated, but they're really still something that you can eyeball, or I'm going to show you how I eyeball them. So there we go. All right, so let's look at this guy. Super excited about this. This one's a little bit tougher. And sometimes you're going to have to go like up. You might have to say, okay, these are the same, and this doubles when I go from 3 to 2. And you don't have to go down that chart. You can go up that chart. It doesn't matter. Okay. So anyway, we're going to find the rate law, and the rate law is going to tell me, rate is equal to K, and then my 2 reactants in this case, and then whatever power they're raised to. That's the rate law. And then I'm going to find the rate constant, that's the K, and then the order is when I'm going to add the exponents up, okay? I wonder if I go forward if it's going to make that chart go away. I feel like it probably is. Okay. I'm not even trying to use their stuff right now. All right, so let's look at this together. All right, let's just do NO first. It doesn't matter the order. But find 2 trials where NO doesn't change. 2 and 3, do you see it? All right. So, I guess that's going to allow me actually to do H2 first. My bad. So, let's do H2 first. So, from 2 to 3, see how it actually gets smaller? I'd rather go bigger, right? I'd rather go bigger. So, when I go from 3 to 2, let me use my pen so the people at home can see. When I go from 3 to 2, this actually goes up by 50%. Don't freak out at all these numbers. Don't freak out. Stop freaking out. Basically, what I'm looking at right here, these are all the same decimal place. Do you see how this is all the same? Okay, just stop. Okay. I'm just going to make this go away. Okay. Do y'all know what half of 150 is? Do you know what 150 plus 75 is? 225. So when this right here increases by 50%, this increases by 50%. What's the reaction order in respect to H2 then? 1. No, it's 1 because they went up by 50%, went up by 50%. Same factor. I have never, ever seen anywhere, even my college work, where it didn't go up by a nice pretty number. So don't freak out at this. You're fine. Anyway, let's go ahead and look at the reaction in respect to NO. So my rate law, if I'm trying to do that right here, my H2, I can go ahead and throw a 1 on that. I hold that steady, okay? If I look from, let's see, where's 2, where these stay the same, 1 and 2? I'm going this way, okay? So let's look, 225 to 900. What's 200 times 4? It's 800. What's 225 times 4? It's 800 plus 225 times 4 is 100. See how I'm doing that little math? That's where it's that's your life goals right there. Forget AP chemistry. That's something that's handy to have. So anyway, this sucker, I know, AP environmental science, middle math for the win, right? But this guy right here goes up by a factor of 4 when this doubles. Okay, so what's going to be the order in respect to NO?
2.
These numbers are, like I said, they're a little bit harder than, the other ones that I've seen. So, if I'm writing this out all pretty and everything, which I guess I can, make that go away. If I want to write this rate law, then it's just going to be rate is equal to K. We don't know K yet, so we won't put a K. And then I'm going to go NO, and that's what we just found, right, as 2. And then H2. And that has a 1. We don't have to write the 1. That's it. Cool? Now, how do you think we can find K? Can we find it? Yeah. Don't we have this? It doesn't matter which one you pick. Just pick one of the trials and then put the numbers in there. Put this number in here. Put this number in here. And put the rate. Guess where the rate goes? Yeah, and you just do math. You can do this part. Yay. Now, who doesn't like, is there some people that are like, I don't like eyeballing this. This eyeballing thing isn't for me. I mean, are you following me on the eyeballing stuff? Because I'm about to show you how it looks like not to eyeball it. And it's so much worse. Like, oh, I don't like math. I don't want to look at and inspect this. I would rather do the math. Well, this formula isn't on your sheet, but here's what that looks like. You want to see? It's super scary. It's very scary. So, don't freak out.
Got it.
That's not bad.
Yeah, so all they're doing, look, all they're doing is writing out the rate law for trial 1 and the rate law for trial 2, and then they're filling in what they know, and then they're simplifying the equation, and then that's the number that you get out. And so we just did that by looking at it. We just did that by looking at it. Yeah, okay. So N for O was 2, which is what we just did. And we used those same 2 experiments. To find it for the 3 to 2, which is the first thing we actually did, you write the rate law for trial 3 and trial 2, fill in the stuff, and then you get 0.67 is equal to 0.67, and so M has to be equal to 1. What? Okay. So fun times. That's what that looks like if you don't want to look at it with your eyeballs. I'm gonna go with inspection. Okay. Yeah. Worst comes to worst. It would be better for you just like if you're taking the multiple choice test, you don't have a calculator. I would rather sit there and be like, okay, 900 and 225. Okay, well those trials, these have to be the right ones. Like 900 divided by 225. I would rather, you're going to have to do that anyway. You've got to divide that anyway. So I would rather do it the way I showed you. And so they're still like cooking on this stuff, still cooking on it. And that's the rate law that I got without all that mess. And so now we can fill it in. I want you guys, do you have like a blank page on a blank page on your paper to do it? Or did they already fill it in for you? Alright, so go ahead and find the rate, find the rate constant. Find the rate constant, pick a trial, doesn't matter, go ahead and try that out. Your friends at home, they're going to have, it would be interesting to see, you know, it really doesn't matter which trial you use. So the rate constant that they got was 7.5, and then notice third order reaction overall. So there's my concentration to the negative second and then negative first. Did you make sure you had those units correct? Did you get 7.5? Cool. So those units are a piece of cake now, right? Cool. So here's where the purple stuff comes back. The purple stuff comes back. We don't have enough colorimeters for this. So what we're going to do, and I think it's going to make a better graph and it's going to be easier for you to understand. If we wanted to do a Beers Law lab for reaction rates, what we would have to do is we would have to take that purple stuff, put it in the colorimeter, come up with a calibration curve, which took us the whole day, that tape, right? And then you mix the purple stuff with the hydroxide. Then you use the calibration curve to get the initial concentration, concentration at a certain time, and concentration at another time. And you can use that absorbance to do that, and then use the Beers Law formula. It's really like a 3-day-long lab, okay? So what we're going to do instead, and I think it'll work really well, is I found a good lab that you just use drops and then you use a graphing calculator. And I think that I'm fine with that. And you get to watch the colors change. Like if you're doing a colorimeter, you don't get to see the colors change. But anyway, so some of this, they're showing you like all the math. And I think it's a little over the top, but I'll take you back through it. Remember when we did spectroscopy, you had a certain amount of light come in, and then some was absorbed, and then you had some transmitted, right? And so the more concentrated, like if we wanted to do that purple, we'd use the color wheel, and the color of light opposite of that, the complementary color for purple is yellow. So we'd use yellow light. It would get absorbed by the purple solution, and then as it turned clearer, more and more of the light would be transmitted. That's how that works. Okay. So anyway, and here's Beer's law. So the absorbance, this would be the value that we'd have to use to find the molarity, is equal to this molar absorptivity. This is unique for every substance. That A, this little A, is unique for every substance. You can't, it's not something that's you can just directly know. You have to kind of solve for it. B is the path length. It's usually 1 centimeter, not always. And then C is the concentration. And this is on your yellow sheet for the AP exam. And they like this. So here, notice B is the path length through the cuvette. That's the little thing with the lid. So I'm going to kind of zoom in on this a little bit for you. Maybe. There we go. What they've done here, this lab, like I said, it would be a bear. It would be an absolute bear. And I think by the time we got done, you would miss the point. So if I just show you stuff turning clear and we do a lab that's a little bit more simple, I think that would be better. Plus, we don't have the color rooters anyway, so it is what it is. If we look at these graphs, what they're doing here is they're measuring that absorbance over time. And the C is this green part of the solution. We can't do anything with a colorless part of a solution unless you have a spectrophotometer. That's the one that can do the ultraviolet stuff. Remember, it does the more complete spectrum of light and ultraviolet light. Anyway, so they are graphing the absorbance, and they're doing this in respect to the green stuff. And over time, there you go. And they did that 3 times. Okay, so I may have to come back to that picture. And like I said, I don't see the value in going through all this again with you. So if I want to find A, I have to find that constant value for this green stuff, whatever it may be. And they're just going to use a data point for anything where C is actually known. And they did that, and I can show you where they did that. They did that for one of the trials, and they found it to be 1, and then they solved for it. And then this is a lot of math. I haven't seen any of this where you have to go through the whole thing. They're just going to show you the results. So I'm very happy to just show you the results and then find the rate order. Like, that's what they're asking you to do. They're not asking you to do all this. And they do some math, and they get the initial rate. This is basically, this guy is that far right-hand column in that chart where you have the rate. And so they're going to find the initial concentrations, and then this is the number that goes in that far right-hand column. And they do it for the next trial. And they get another rate. Notice that these are already like twice as much, right? You see that happening? And then they get another rate. So they have, no, not yet. There, they get another rate, okay? So they basically have gotten the rate for 3 different trials. And then you can put all that in a chart, which is where I'm going to pick it up. Yay! Okay? Now, this is what they're going to give you on the AP exam. I super duper doubt that. I've never seen one where you have to go through the whole process. And if there is stuff where you have to go through the process, I say we tackle that in like March. Sounds good? Right, that sounds real good to me. Because I already made your test. Like, I already know that you don't have to do all that. So, I'm cool. Yay. Yeah. But you do have to do this. So, we're going to make a chart. And don't freak out. Like, this is the rates. And those initial values, look. Those initial values were just right here. See? BC initial, BC initial, BC initial. That's all. That's all it was. They took the rates that they saw for and put them in a chart. So what I want you guys to do is see, do you have some blank parts? So go ahead and see if you can write the rate law for this for me. I want to go through the whole thing. Write the rate law, and you know what? Go ahead and solve for the rate constant. Knock it out. Give me the overall order. I think you can do this. Right? You totally got this. Plus, I'll help you write it in paper. If you don't know, just like raise your hand and I'll come over there. If it's close enough to twice as much, then you can assume and round. This stuff's clear again, and the whole giant Bible is not clear, so I think we're good.
Yes.
Yes.
If we come in tomorrow, it's clear. I'll be like,
How much is Crystal Violet
I
cost?
don't know. I didn't even know it took a while. I was like, I honestly went to the lab during the thing. I turned on the vent hood, and I was like, I guess this is it. And I took all the drops from there, and I waited a different color, and I was like, I'm going to do that. But then eventually it did change. So. It's labeled like cobalt chloride or something. I'm going to kind of start working on this on the board. Don't look up if you don't want to look up. Look up if you do. I don't have the answers. Let me know if I mess up. That's kind of a joke, but also kind of serious. What? What happened?
Did you say to solve the constant?
Yeah, solve for the rate constant and then tell me the overall order. So here we go. Well, that's really lame.
Yeah.
Yeah. Okay.
I thought I got it wrong. That's like most things. I mean, it's usually complicated.
And once you go ahead and I should show you this. Like I'm just doing the first trial. As soon as I write that capital M, I don't write a bracket. You do one or the other. And I'm not I'm about to put my units down. So I'm putting a capital M. I don't do the bracket. You do one or the other, not both. Okay?
I feel like I did it so hard.
What? You're super disappointed?
No, I feel like I'm doing it right. I mean, that's all I do something. That's usually how my life goes. What is this? Is this Obsidian?
Yes, ma'am.
Oh, I'd rather have some of these.
This is just 0.01, right?
Yeah.
Okay. And so that ends up being, what, to the third power? To the second power? Or negative second? Yeah, okay. Man, that scientific notation stuff, that stuff is, that's handy. That's super handy. So,
This is like
and then,
all the time.
that's,
The scientific notation stuff. That never goes away.
it sucks when you're having to learn it.
Should we leave the answer?
So this is second order, so I'm going to have to have a -1 and then an S -1.
For homework, we're going to be doing practice problems.
Yeah.
They're not that bad, though.
I think that's about it, ain't it?
Yes.
Alright, how's that looking?
Good to start.
That's what I got. Okay, cool. Does anybody have any questions about this?
No.
I would give a lot of money for somebody to teach me this. Like, instead, you know what I mean? Like, I wish that somebody had taught me.
Did you have to do the math?
I had to teach myself, and it was the struggle was real. I'm just going through this. See, if you just read a book and you don't like have somebody to water it down for you, it's pretty rough. It's scary. So that's it, right? Yay! All right. So there is a little bit of the A, B, C stuff in the practice problems, but it's pretty chill. Okay, and you got an answer key, and you got 15 minutes. and you're gonna finish these 8 tonight. Okay. I do want to do one sticky note for number 2. Let's see which one matches that. Where's our nice little chart? Let's do number 5. Will that fit on there? Yeah. 5 will fit on a sticky note. So, you're going to do 2, 3, 4. You're about to do 5 right now, 6 and 7. So, you're going to do the rest of this sheet. You already did number 1.
So we don't have to do 5.
5 is going on a sticky note up there. I got some sticky notes if you need one.
Are you going to check our games?
Yeah. I'm going to grade your quizzes real quick.